Welcome everyone. We are back after almost 2, 3 months. But this time we have very amazing lineup of speakers for fall. So I would encourage everyone to join, engage in the topic. And as always, we put the talks on our YouTube channel if the speaker allowed. And I just shared different information, website, YouTube, and Slack channel. You could also join our Slack channel. There are some job opportunity Slack chat. So yeah, I think that use this opportunity to be connected to the other fellows in the same topic. So yeah, just a couple of announcements. I will update the speakers every week, so keep tuned. So maybe I give the stage to Sam.
All right, so it's amazing line of speakers this season, so I do recommend. But our first speaker is our host, so it is my pleasure to announce Pooneh. So actually, we won't probably most of you are we went through the ICASP night, so let's see. So anyway, so. Pune has been doing her PhD in Concordia University and Mila, working with Mirko and myself. We just went through the ICASP deadline last night. So yeah, and I mean she's a leading expert, I believe, in audio tokenization these days, and we are really privileged to hear about the details about what's happening in audio tokens, especially if you are working in the domain. Like, you shouldn't miss this talk. And without further delays, I leave the stage to Pune.
Okay, thanks. Thanks for the nice introduction. So yeah, since the topic today is kind of very dense, let's just go directly to the talk. So today I'm going to talk about our recent paper, which is just published at TMLR Journal Conference. The title, as many of you might know by now, is Discrete Audio Tokens More Than a Survey, which we are going to talk why we choose this title actually. So this paper is a collaboration with a very amazing team. Many of them, I think that I have seen their name in the audience. So I want to especially thanks all of them, especially the core team who are doing the main experiments, and also the great advisory teams that we have. So this work is done with collaboration with many universities and also from different big companies, so we could have perspective from different places. So maybe we could start with very short background, not very detailed one. So when we talk about discrete tokens, it means that it is one kind of features that we want to pass to the models. And if we want to have a taxonomy of a feature extractor, we could say that we start with signal processing features like FBank, go to something like adding only CNN for extracting features, and then recently something like self-supervised learning, which is used to be continuous, like WAV-LM, Hubert, wave-to-wake. And then in a couple of last years, people try to see how it could work to use discrete alternative as a representation to pass for the speech tasks. So how it works, it is like an overall architecture. For sure, there are lots of different variability, which we are going to talk. It is basically the input, some sort of an encoder that gets X, and as an output, it creates the embedding ZT, and then it goes to some sort of a quantization. It could be any different quantization, creates Z hat, and then pass it to the decoder to reconstruct the audio. And for sure, there are like lots of different losses that could be applied to improve the performance and fidelity of the reconstructed audio. So why audio tokens? So audio tokens, first of all, what we expect from these tokens is that they should be semantically rich. They should preserve lots of details about audio, exactly like the continuous one, preserve context, paralinguistic, a speaker identity, emotion, prosody, everything. And why discrete tokens? Like, there's a question, I think, why discrete tokens are important. First of all, it has the benefit of a storage. So you could just store the indexes regarding the audio, and it could help with the storage. If originally the main purpose is that if you want to transmit over the network, transmitting this index as this discrete index is much easier. Then one of the main application of these discrete tokens is basically the audio generation task, that instead of having this regression task, instead of trying to predict the continuous vectors, now you have this finite vocabulary and you could convert from regression to classification, which is easier. Although nowadays people argue about that. It has a faster inference. And also because this discrete natures of the LLMs, it is easier to basically integrate these tokens, the audio modality, with the language model. Again, this point could be discussed, like many of these diffusion models are recently introduced, but it is one of the things that, like one of the argue for discrete tokens, actually. So what is the motivation behind this work? Traditionally, these discrete tokens are done with handcrafted features and using domain knowledge. And then people said, okay, maybe we could use deep learning approach to do this neural codex. And then basically from 2021 kind of forward till now, there are lots of new audio tokenizer proposed. If you are attending interest speech, probably you have seen a bunch of them. So there are many, many of them. So what happened is that at the previous interest speech, a team of researchers from university and industry gathered together, and we said, okay, now it is a good time to come up with a very comprehensive details about the audio tokenizer, the techniques. Also, there are lots of benchmarks proposed from each of these tokenizers. And we are thinking maybe now it is a good time to unify everything and have some sort of a conclusion and comprehensive takeaways from all of this discrete tokenizer that is proposed. So what is our contribution? The first one is the taxonomy, which is the survey part. Then we have a benchmarking. For the benchmarking, the point is that we benchmark different off-the-shelf tokenizers. So already there are lots of benchmark in the literature for evaluating audio tokenizer. Each of them actually try to look at different perspective of tokens, like reconstruction, downstream evaluation. So basically, we want to see what if we unified all the results and have a unified setting for all the benchmark, like same tokenizer, same data set and everything, and see what are the conclusion that we could make from all of this benchmarking. So basically, the output of this section is like, from all the off-the-shelf tokenizer, which tokenizer is best based on your task and based on your data domain. And then the last part is about ablation study, which is mostly about if we want to compare tokenizer, each of those tokenizer are trained in a very separate, factors, like training data, number of epochs and everything. So in ablation study, the point is not using the off-the-shelf tokenizer. It is about if we want to train a tokenizer from the scratch, what are the factors that we need to take into effect? And we try to basically fix everything, just change one thing and see what is the effect. So it is about the last part. And we try to target 3 different domains of speech: general audio, like dog bark, background, and music. So I will start each sections. I will go through each of them broadly. We could not go over all the details, but after each section, I give time so you could ask questions about that. So traditional taxonomy of speech discrete tokens was something that I said compression or acoustic, which is basically encoder decoder trained to learn how to reconstruct the audio. Then it is semantic, which is like getting SSL models, apply k-means or any types of quantization on top of that. And then something like hybrid, which is basically combining these two approach, like distilling information from semantic to the acoustic. And this is like the main taxonomy that people used. Still, I think that we could use it. It is like a very broad taxonomy, but also many people are not very happy because of many reasons that I'm going to talk. So what's the problem? So if we basically, this common division has some limitation. The first one is that when the tokenizer evolved, basically what happened is that semantic tokenizer could capture could do well in generative tasks, and on the other hand, acoustic tokenizer could perform well sometimes in semantic tasks. So this overlap blurs the boundary between these two categories. And finally, this broad category kind of is not enough when new tokenizers are proposed. It could not capture all the key architectural differences and practical trade-off. That's why we suggest a new taxonomy. So we try to come up with a comprehensive as much as possible and try to look at this tokenizer from different perspectives. So we have five main categories of encoder, decoder, quantization, training, target domain, and streamability. So let's first talk about quantization. So basically for quantization, we have two main subcategories. It is about, okay, what are the different techniques and all the different settings that we have when we want to do the quantization module? So first, it is like the algorithm used for quantization. And the second subcategory is what is the bitrate, if it is fixed or if it is adaptive. So quantization, we're going to go over them very briefly. So for algorithm, we have k-means. Mostly it is like getting one SSL model, choose one layer or multiple of them, apply k-means on top of that, and use these indexes as the discrete tokens. Then we have residual vector quantizer, which is like the common approach that basically you have multiple code books, pass the input to the first code book, get the residual from the embeddings generated and the input, pass the residual to the next layer, and then continue till you reach your end of your code book. So you have multiple code books that would capture, parse, and find information about your idea. Then it is single vector quantizer, basically same as RVQ, but then people argue maybe we don't need all of these different code books. There are redundant information. Maybe we could use only single layer. And it is easier to integrate that actually with language model because of the frame rate. And in order to compensate for the potential loss of the information, they try to increase the vocabulary size actually. Then it is group vector quantizer that basically you get a Z as an embedding and try to split it into specific groups and apply quantization on each group separately and then concatenate everything together. Then this is completely new category of finite scalar quantization, which is been applied to vision before. But then people said, okay, instead of having these learnable embeddings, we could basically map each dimension to a fixed set of scalar values using some non-linear activation function like tanh or something. So there's a range and we try to map it to the range. Multi-scale, it is like, okay, RVQ, instead of each layer, each code book has the same resolution. Maybe first we could do the first layer with more fine-grained, with higher resolution, and then once we go upper in the layer, we could capture more coarse with more or lower resolution code books. Cross scale basically again seems like RVQ, but instead of only apply vector quantizer at the end of the encoder, it has the quantizer for each encoder and decoder steps. So you could hierarchically learn quantization for each step, and it could help the reconstruction. Then product quantization, basically it is what you use in many of the self-supervised model. Again, kind of similar to what we have in group quantizer. It tries to split and then use random projection instead of learning the code book to discretize the output. Mostly there is no decoder applied to them. It is mostly used in something like best RQ or UCM. Then another subcategory is bitrate. Bitrate could be fixed. It means that basically the bitrate is determined by the number of bits, like the number of code books, numbering, and it is fixed. The next one is adaptive bitrate. It means that you could use some sort of a Huffman encoding or something, or entropy-based coding that basically select the bitrate based on the frequency. If the frequency of the tokens in your data set is high, then it tries to assign lower bitrate. If it is rare, it tries to assign more higher bitrate so it could capture all the details that it hasn't seen before. One thing that I want to mention here is the difference between adaptive versus scalable. Adaptive is what I said, like Huffman encoding, entropy-based coding. Scalable, it means that you train with fixed bit rate, but during inference, you choose the number of codebook to be used. So it is what we call as a scalable. It is different from adaptive. There is the term that sometimes people use interchangeably by mistake. Then for encoder, the other category is encoder-decoder, which has two subcategories of architecture and representation. So for architecture, encoder and decoder could contain different components. We here just try to focus on very basic components. So for example, it could be more sophisticated, but I think all of them could go under the hood of the same category. So convolution, combination of convolution of RNN, it could be LSTM, GRU, anything like that. Only transformer and convolution cross transformer. So more sophisticated, some things like conformer and everything could be easily categorized somehow in some of these models. The other things is that the encoder and decoder could have same architecture or could have different. So maybe they could mirror the same architecture, just doing upsampling and downsampling, or sometimes people prefer to use different encoder and decoder. Then the other category here is about representation. So the input could be the time frame or it could be frequency domain. The output could be time domain. So we basically try to upsample and directly generate the waveform, or the decoder could not focus on upsampling, it try to do the time frequency domain and then use inverse short time Fourier transform to do the upsampling and create the features. I don't know why I get that their meeting is going to end in 10 minutes. I'm not sure. Then it is about the training paradigm. So the training paradigm, it has three subcategories, which is main objectives that all of these tokenizer are trained, the auxiliary component, and if the training is joint or not. So for joint, it is separate training. It means that if the encoder and decoder are optimized separately from the tokenizer. So something like k-means, or whenever you have hi-fi GAN, the decoder is trained separately, the encoder is trained separately, and something like that. Joint, it means that everything is like encodec DAC, everything's are optimized. For sure, people like try different strategies, sometimes freeze one part, train, continue optimization through the entire after that. So there might be multiple stages, but there are the two broad categories. Then the training objective, these are the losses that could be used in many of these tokenizer. Not all the tokenizer use all of them. One is reconstruction, the difference between input and predicted output. Vector quantization, something like, for example, a commitment loss that we apply. So we want to make sure the output of the encoder is similar to the predicted embedding after the quantization. Adversarial loss, which have a discriminator and the generator, which basically the normal adversarial loss. Feature matching, so basically sometimes you have these discriminators and you basically said that, okay, features of different layers of this discriminator, feature of the actual audio and the predicted audio should be close to each other. So it is one other loss that sometimes people use. If you have a diffusion-based models, you have a diffusion loss. And mask prediction, especially when you have this SSL model, it is like you mask part of the input, try to predict the quantized output of this mask prediction. Then these are the main loss, but for sure we could also have some auxiliary loss attached to each of them. One of the auxiliary loss is disentanglement. So people are interested to see what happens if you could disentangle the feature representation into different components. Each component is meaningful enough. For example, one component is more responsible for a speaker, one is for prosody. And different techniques are used. It is mostly like you have different branch or different way to disentangle your feature space. Then it is semantic distillation, which is used like very common in something like Mimi, a speech tokenizer. Basically, you have your autoencoder And then you have some sort of a SSL, Babel, and Hubert, and you try to distill the information to the first layer and sometimes to the output. It depends. It could be different based on model to model. But it is like you try to make the output of your quantization very close to the information, to the output of the VAVLM. So you could make sure that it contains enough information. So it is what we call the semantic distillation. So far, all of them are kind of unsupervised. And then we have supervised semantic tokenization. So instead of unsupervisedly try to reconstruct the audio and everything, you could add actually supervised lots on top of the decoder or on top of the vector quantizer itself to make the tokenizer more semantically rich. So this is another component that sometimes people use. For example, in past, they use different auxiliary. In S3 tokenizer, in Cozy Voice, they use ASR decoder. So different way to encode semantic information into your tokenizer. And finally, we have streamability and domain categorization. So streamability is like if the model is able to generate audio in real time without seeing the features. And target domain is like the type of data that the tokenizer is trained on or claim that it could work well on that domain. Could be a speech, general audio, music, or combination of all of them. So yeah, we are done with our taxonomy section. We provide the database of around, I think, 70 tokenizer in details, having features for all of these tokenizer. You could check our website. We put the interactive design there, so you could take a look, try to look for your tokenizer, search and everything. And if you have a new tokenizer, we have a link at the end. Please submit your tokenizer, and we would like to update our database so everyone could see the different tokenizer on the market. So maybe now it's a good time to have a couple of questions before going to the benchmark part.
Yeah, so there is one question. Is it acceptable to refer to the outputs of an audio encoder, for example, a VIT over spectrograms as audio tokens, even though they are continuous embeddings by analogy with the audio tokens of a VIT, which are also embeddings rather than discrete units?
So basically it is, yeah, at the end we have the embedding, which is continuous, but it depends how you're going to use your tokenizer. For example, if you use this tokenizer to pass it over the network, then you only use these indexes. You don't use the embedding. Or if you want to have a speech language models or any acoustic language model, when you do the prediction, you basically predict the token ID, not the embedding. So still there is some sort of a discretization terminology on that. The first part is about taxonomy, and now the second and third study is basically what justified the name of the paper. So discrete audio tokens more than a survey. So this is the more part. So the second study, we do benchmark evaluation. As I said at the beginning, it is about what happens if you take off-shelf tokenizer and try to use it, and we want to evaluate this tokenizer from different perspectives. There are a couple of different benchmark provided for that, and we try to basically ask all the people who are involved in this benchmark to collaborate in the projects, and then we try to come up with this benchmark evaluation part. So basically our benchmark evaluation has three main components: the reconstruction evaluation, downstream, and acoustic language model, which I'm going to talk about each of them. So for this section, for sure, we could not benchmark all the 70 tokenizers, but we choose list of tokenizer, and our criteria for choosing them is, first of all, it should be publicly available because we want to use off-the-shelf models. We care about the diversity of quantization, like these two is RVQ, semantically distilled, k-means, finite scalar, and singular. And then we want to make sure that we choose tokenizer that could cover different domains of audio, music, and speech. So we prioritize tokenizer that has at least a checkpoints that cover some of them. So for the reconstructed evaluation, what happened is that basically we want to basically evaluate the output of the token, the decoders, the reconstructed audio. In order to do that, we use two benchmark, Codec Superb and Versa. There are a bunch of different evaluation metrics that applied on top of that. There are some of them signal level, so something like UTMOS, SDR, or something like that. And then some of them is application levels. It means that it is not on the metric is like having a separate model on top of the reconstructed audio, for example, whispers, and try to see what is the border error rate, or for the speaker similarity, doing the same things. So these are the performance that we have seen for a speech among all of the different tokenizer that we have. We try a different number of code books. So for example, if the tokenizer offer multiple code books, a scalable multiple code book, we try to choose different of them. And basically what happened is that we could see actually when we have a higher number of code book, the reconstruction is better. This observation is important when we go to the downstream evaluation. We have the same table with some of the metrics for audio and music domain. For the sake of time, I just talk about the general takeaway of all of these experiments. So first of all, audio tokenizer should be evaluating beyond traditional waveform fidelity measure. There should be lots of different metrics that we could capture different parts of the audio tokenizer. And sometimes some of these metrics doesn't show good performance, but when we listen, when we have a subjective evaluation, actually their performance is not bad. The second part is about downstream evaluation. So here, we don't care about the reconstructed audio. We basically want to see how rich is the quantized version, the quantized output of the quantizers. And that is where we just try to explore. The intuition behind that is because basically sometimes the good performance might come from a strong decoder, not actually rich tokenizer. So we basically remove that and try to see what is the performance, how rich the information of our quantizers, by basically train a very lightweight probing head for different tasks on top of this discrete unit and see what is the performance and compare it with continuous baseline. In order to do that, we use DAS baseline. So we use lots of a speech discriminative, a speech generative task, music, and general audio. So this is all the list of the tasks, the data set that we use, the architecture, and the metrics. So here it is the result for a speech. What we have observed, like the very main takeaway, is that when we have something like the encoder is something like SSL, like WAV11, then we apply K-means, actually we have a better performance, which is different from what we have seen from reconstruction. And reconstruction in codec and DAC has a better performance on the reconstruction basic. Here, when we want to capture semantic, it is important that our encoder basically train with supervised, with semi-supervised model or something like discrete WAV11. The other observation is that different from reconstruction, when we increase the number of code book, we basically see downgrade in the performance. So some things with 8 code books give the best result. So there are the difference between these two evaluation. Kind of the same pattern are observed also for generative tasks. For music and audio, basically, we don't have any discrete, any like supervised model that we use or semi-supervised model that we use like WAV11 or Hubert, but we basically try all the tokenizer that could support audio and music. And even though DAC had a good subjective evaluation, most of the time encodec has a better performance. So again, very broad takeaway of the DAS benchmark is like, again, let's return back to now broader category of tokenizer, acoustic, semantic, and hybrid. The reconstruction is better in acoustic, lower in semantic, and when you have hybrid, like when you have a semantic distillation, something like, for example, Mimi or a speech tokenizer, it basically kind of the moderate between two. One important thing is that when you have a low resource robustness, for example, we have some data set with Welsh or Basque language that are kind of low resource, and we could see that basically this kind of acoustic tokenizer has a really bad performance. Then Model scalability, actually DASP, we try different probing head. We try low, kind of the deep and lighter models. And when you work with acoustic, you kind of need larger model to make it converge, and you need more data. So scalability in acoustic tokenizer is more important. For semantic, you could converge faster. And finally, for efficiency, you could basically encode acoustic tokenizer more efficient, because you could choose the encoder that you want. You are not basically limited to something or VAVLM or something. So they are more efficient, but the price is that the semantic capture is less than acoustic tokenizers. The final benchmark evaluation is about acoustic language model evaluation. So basically, we get the discrete tokens and we train a language models. It could be a speech, audio, or music. And we try two different settings. The one is unconditional generation, which you prompt the model. It is like a content to ask to continue the generation, or you prompt it with text and ask it to generate some samples based on the text prompt that you have. In order to do that, we use Zero Resource and Salmon as a benchmark. So the first part is a speech language model. So we train everything with autoregressive model. We don't include any diffusion-based model here. It is mostly autoregressive one. What we observe is that, again, when you have semantically, like tokenizer with semantically rich, like K-means over Hubert, VAVLM, or something with semantic distillation, on task that needs semantics, that needs capture semantic, they have better performance. For acoustic consistency, sometimes we could see that other tokenizers like the hybrid one or even the encoded one could have better performance, and the same things with semantic and acoustic alignment. So main takeaway, semantic and acoustic performance vary significantly across tokenizer types. The best model is Hubert, which is basically Hubert model, K-means, and then train based on that. But if you train a semantically distilled, like me, or a speech tokenizer, and if you assign more weights to the first layer, which applied the distillation on that, then you could get promising result as close as Hubert. Overall, there's no single tokenizer that could perform well across both spoken and acoustic tasks. Then we have text-to-speech, which basically we use Valley. We could see that for word error rate, we actually seen again VAVLM perform better. When we talk about something like acoustic measures in codec or speaker similarity that needs finer level information, encoder works better. So again, a strong TTS performance remains challenging. It depends on many conditions, especially if you want to work with acoustic tokenizers like encodec, DAC. You need to really scale the data and scale the model. Otherwise, it would not be converged. That's it. Then the next settings is the audio generation domain. So basically what happened, they use AudioCraft. I think Galil is here. They use AudioCraft, autoregressive models, and then try to use AudioCaps data set and try to do unconditional and conditional generation. And basically here we try to see what happens. For example, if we use encoder train only for audio, encoder trained with music, and encoder trained on 3 different domains. And we trade different number of code books. And as a higher baseline, we also capture the reconstruction performance. So what is the finding is like most all the time when you have domain-specific tokenizer, especially for audio, you could get better performance. So it is the importance of in-domain tokenizers. Not necessarily the better reconstruction performance does not necessarily mean that you have a better performance in modeling, as you could see. And it is not as much metrics, evaluation metric as a speech for music or audio. So there is a need to come up with more robust evaluation metric. We do the same things for music. We use 2 data sets of music, caps, and FMA. and basically do the same setting, text condition and uncondition. Kind of the takeaway are very similar to each other. Domain-specific tokenizer is better, and especially for for music, since it needs lots of details to be captured in music, it is important to have a higher sampling rate and multiple codebook tokenizer. General trend, we try to rank the different tokenizer based on different category of the task, average over the task, and rank them. The main takeaway, there is no tokenizer that consistently outperform all the accesses, and the performance is strongly task and domain dependent. So if you have a task and you have a domain and you want to choose which of the shelf tokenizer you want to use, you need to really think about what is your data distribution, what is the amount of data you have, and what is the model that you want to use. Then you could have better understanding what is the best tokenizer for you to use. For example, if you have a limited data, maybe something like encodec is not a good choice for you. But yeah, it relates to many different factors. So maybe we could answer some question before we go to the last part.
Yeah, so the number of questions. So the first one is, what does this mean that some tokens have low reconstruction score but perform better for many downstream tasks?
So basically, it is like if we compare here, basically we have this reconstruction. For example, we have seen that encoder have the best score, for example, in SDR, and many of these encoder and DAC together have the better performance for reconstruction metric, like when you apply these metrics on top of the reconstructed audio. But when we try to see what happens when we apply probing head on top of the discrete tokens, not the decoder, not the reconstruction, basically we could see the different trend. This time, the tokenizer with, for example, VAVLM, k-means on top of VAVLM have better performance than encodec.
All right. Next question. What is the intuition behind k-means and low number of codebooks working better in downstream tasks? I mean, is there an intuition or is it purely experimental?
Kind of both. It is like when you have semantic, you don't really care about all the different details of it. For example, when you have ASR, you really care about phoneme detection. So you don't care that much about all the details. So when you add more details into your tokenization, it means that you make the model harder to model. So it is harder to model, harder for the model to converge. But we need to also mention that if that is the case, it means that if you scale the model and scale the data, you could still get a better good enough result. So basically, these models are like models with, for example, k-means on top of VAVLM. It is easier to converge because they are richer in information. So you don't need to just train very complicated architecture on top of that to get a good result.
Great. Another question. Having strong decoder can reconstruct the waveform well. Does it mean the encoder part or the tokenizer with less number of tokens can perform on par with a strong decoder?
It could be the case. We don't have any result that I could show here, but sometimes you could see that same encoder, and then if you change the decoder, replace it with something stronger, sometimes you got better results. And it is kind of intuitive. Your decoder is all the losses, all the reconstruction loss, scan loss, and everything's applied on top of the decoder. So it could be a case that if you replace your decoder with a stronger one, you could have better performance, even with a weaker encoder.
Yes, yeah, that's, even though like the bandwidth is like bitrate is smaller. How do the semantic tokenizer have higher downstream performance as compared to acoustic on generative tasks like noise suppression or speech enhancement?
So actually, that was also surprising for us, especially for generative tasks. But I think that you need to take into account that we remove the decoder parts. Only we use decoder to reconstruct the audio, or the probing head are applied on top of the representation. And this semantic tokenizer, like k-means on top of the VAVLM, has basically more rich information. So it is easier to train the model when your input is more informative.
All right. The next one, which layer of Hubert is best? The output layer or an intermediate one? For example, the one used to extract discrete units in the second iteration of Hubert training?
Yeah. So basically, it depends. Most of the time, people use layer 6. This is not in the paper. This is another paper in last year in speech that we try combination of different layers. And basically, when you use combination, you could get better result. And it is basically task dependent. For example, if you want to work with a speaker task, you need to go for lower layers because it contains more acoustic related information. If you want to work with ASR, maybe higher layers information is more important. So it kind of depends on the task, but as a rule of thumb, people use the middle layer, which is layer 6.
Mm-hmm. Great. So another question, was any of the tested tokenizers working in the frequency domain or all take in raw audio? If yes, did you see a difference in the benchmarks between time and frequency domain tokenizers?
Good questions. We didn't do like on the evaluation benchmark, all of them work on time domain. So we don't have any comparison between time and frequency. But it seems that when you have a decoder that works on frequency domains, it works better because it don't need to be busy with all the upsamplings and everything. But we don't have any result to show in the benchmark regarding that.
Mm-hmm.
Maybe we could,
Okay. Yeah, there are two more questions, but if you want to continue, I don't know, maybe you can.
maybe I will continue and then at the rest we could
Yeah. Yeah.
okay. So, and the last part is about to the slide. The last part is about ablation studies. So as I said, if we want to train a tokenizer, what are the factors that we need to take into account? For that, we use ESPNet codec, and we try to see the effect of different factors. First of all, we see different quantization. So the base means that we use the DAC architecture. It doesn't mean that it is not pre-trained with DAC. It is just the architecture of encoder and decoder. We tried RVQ, SVQ, single vector quantization, finite scalar quantization, and k-means on top of VAVLM as an encoder here, and we trained the unit hi-fi GANs. Then it is one ablation study, the effect of quantization. Then we try two different sampling rates, 16 and 44 kilohertz, and see what is the effect. The other ablation study is that we keep everything the same, and we try to train the data with domain specific and combination. Like we train only with a speech, only with audio, with music, or with combination of all three. And finally, we also, maybe it is also part of the quantization method for speech, we also consider the variation that we also distill information from VAVLM. So basically, it is the result that we got for a speech. You could see we have different tokenization strategy. The plus means distillation is added. We compare between 16 and 40 kilohertz and different training data that they have. We do the same things for audio and music. But what are the insights from all of this big table? Data domain. So in all the experiments and all the quantization, what we observe is that this kind of what we also observe in acoustic language models. When you train a tokenizer on in-domain data on one specific domain, it performs better than multi-domain training. So next time, if you want to compare a tokenizer which train on multi-domain, like in codec, with something like, for example, big codec or something that train only on a speech, you need to take into account that this might be the confounding factor that caused the difference in the performance. It might be one of them. Sampling rate, it kind of depends on the quantization. The RVQ always benefits when you increase the sampling rate, but sometimes in some of the quantization, you could check lower sampling rate is better. So it is something that you need to optimize when you want to train a tokenizer from scratch. Based on your quantization, what would be the appropriate sampling rate? Distillation effect, basically, whenever you distill information, you have better performance in metrics that need semantic extraction, like ASR, but it might hurt the performance of the reconstruction. So there is a trade-off between that. The problem with distillation effect is that we only have such models for basically a speech, and there's no tokenizer, at least not that I'm aware of, that try to distill information from self-supervised model from audio or music. So you could not generalize well when you distill information from something with vowel and from a speech to music. The quantization method, it seems that RVQ performed the best when every other things is the same and only the quantization is the confounding factors. And quantization performs the best. And in some cases, we could see also finite scalar quantization have a good performance. We released some of the samples related to some of the examples on our website. Please take a look. Maybe I talk about conclusion and future direction, and then we could answer the questions. So we have done all of this analysis, what we learned, but what should we do for next steps? What is the future direction? So here we just talk about some of the limitation and some of the possible future direction. First things is a scaling limitation and generalizability. So basically here we use very moderate model size or data size. If you scale it, for sure, you could get better performance. That is for sure. Maybe if you increase it a lot, you kind of get the same performance for all the tokenizer at the end. But it is not the main point. In many real world scenarios, you have limited data, you have limited resource. So if you want to work with this tokenizer, you need to make sure which tokenizer could work in moderate size data set and models. We discuss about it. It is not necessarily a direct correlation between the performance with reconstruction and down performance. Like when you have a codec superb and DAS benchmark, sometimes the observation is different. Like higher code books cause better performance in reconstruction since it captures all the details, while we need maybe medium or lower number of code book to capture all the semantics more easier. From ablation study, we see that maybe the difference between different tokenizer not necessarily comes from the quantization or maybe not comes from the specific way that they train. There are different factors that we need to take into account when we want to compare the classifier, the different tokenizers, like what we have discussed already. What we observe, there are a gap between what reported in some of the paper and the benchmark, which is kind of reasonable. There are different settings, sometimes different data set, but there's something that we need to mind that we could not always reproduce the exact same result. When you want to have some sort of a distillation, right now it is only applied for a speech domain. Maybe there's a need as a future direction to also apply distillation for music and general audio. When we compare discrete and continuous representation in DAS benchmark, there is still a big gap between if you pass the continuous representation, if you pass the discrete representation. So better tokenizer need to be introduced to be able to close this gap. Right now, we have seen there is no tokenizer that could beat all the accesses, like reconstruction downstream. So maybe that's a need, to have a tokenizer that could work well across different evaluations metric. And also, maybe there is a need to have a tokenizer that would work on different domain, mainly because at the end, the goal is we have this multimodal model that would think, reason, speak, and it is important that we have one tokenizer that it could understand everything. And finally, when we talk about discrete tokens, the first things comes to mind is TTS and voice cloning. So we need to make sure we talk about trustworthiness, the misuse of this voice cloning and fake news and everything. So these are all the limitation and future direction that we extracted from all the observation that we have from the survey. So yeah, that's all. Now maybe we could answer some of the questions.
Okay, so quickly, one question is from Anil. For speech language modeling tasks, how do you experimentally practically reconcile having different number of tokens from different tokenizers? For example, our wiki tokenizer, like speech tokenizer, Mimi will output 8 codes per time step, whereas Hubert gives you a single code per step. Maybe a naive question. Thanks.
So basically, when you have a different if I understand the question well, if you have a different number of layers, basically you could apply this delay pattern. So condition on the previous code book, you generate the next code book and continue till the end. And then basically, for example, if Hubert only have one layer, in codec has 8 layers, it is one of the things that we want to compare the performance, actually. It is one of the factors that we want to see. What is the effect?
All right. Any further questions, Anil, or if not, we'll go to the next one. Is there any reason why a low reconstruction score does not lead to better downstream performance? Are there any other implications because of this? Does this mismatch relate with anything else, like the losses, whether adversarial or not, for example, architecture, so on and so forth?
Maybe. Personally, I think the main issue when we have a reconstruction is that maybe all the good performance come from the decoder. It is the intuition that I have. Maybe it is wrong. And maybe not the tokenizer, the encoder or the tokenizer itself, maybe not very rich. It is the decoder that try to do all the tasks. So it is my intuition. It is mostly because of the strong decoder that you have. Um, Maybe.
Okay, I mean, it's sort of like I mean, earlier, like for example, people were using autoencoder as reconstruction, like as a representation learning thing. But um, now like people more like use like SSL type encoders,
Mm.
right? Like,
Yeah, yeah.
but we don't have the guarantee that the SSL encoder will lead to like a yeah. Um, so, anyways, another question. Do you think one can model a tokenizer to be task specific by being aware of the requirements of the downstream task it is being used as? Imagine a system prompt like situation for the tokenizer, so it only produces the most relevant for the downstream task when it is interested in. Maybe that could be winner in all domains.
So yeah, maybe it could go like if you want to have a very expert tokenizer on a specific domain, one way is to basically use supervised lostness, maybe on top of that. But now, from what we have seen in the survey and different analysis that we have, there's no tokenizer that could perform well. There are lots of factors that need to be taken into account, like the data domain, for example. Maybe one thing is that maybe fine tune the tokenizer with a specific data domain that you have. So like maybe the general answer is that you need to think about different factors that could have effect on your specific domain.
Okay. And then one last question. I mean, if you have like all people who ask questions, like if you have follow-up questions, then feel free to, continue on the threads. Uh, if you have to use a tokenizer for a specific task, which tokenizer will you use? Some question like this.
So again, it depends on the task. If it is ASR, for example, I use k-means on top of Babel. If so, it really depends. Like for example, if it is acoustic language models, I would like if it is audio language model, I use the encodec that is trained on audio only. So it really depends on on the task and the data that you have.
Mm, yeah, makes sense. Last question. Can you talk more about the point that just moved. Can you talk about the point that sometimes evaluation metrics like PESQ, STOI, MOS, etc., may show a poor result, but the subjective evaluation shows that the performance is good. So like this kind
Yeah,
of thing too.
yeah. I think that sometimes you could see that the performance is not good and then you listen and then it is not bad, or sometimes vice versa. I think maybe one of the reasons is that many of these metrics might be very dependent to the alignment, to the frame rate, and the mismatch in the time and everything that could cause this issue. Uh, Maybe that is one of the reasons, but I'm not sure about any, maybe if someone else, I'm not working on the evaluation metrics in details, but I think it is one of the reason is the mismatch between alignment with different frame and everything is that many of these factors take into account.
Mm-hmm. Mm-hmm. Um, yeah, there's a follow-up message on the thread. I'm also curious about this. Is it because of stuff like hallucinations, change of speaker characteristics? Uh, Any ideas about
I
that?
don't understand the question, sorry.
I'm also curious about this. Is it because of stuff like hallucinations, change of speaker characteristics? Like,
The difference between reconstruction,
yeah,
subjective and objective,
yeah, yeah.
it might be. I'm not quite sure.
Uh-huh.
It might be, but I'm not sure. There's not.
Okay. Okay. All right. One last question. What is your opinion about very low bitrate transformer-based tokenizers compared to more standard convolutional-based models? I'm especially surprised about the generative behavior of these models, and most of the times the output doesn't sound close to the input signal at all. Reverb is gone, background is gone, etc.
So basically, for sure, there is a trade-off. When you have a very low bit rate, you're going to lose some of the performance. So it depends what you want to use them for. For example, if you want to use them for a streaming, then it is important. If you want to use it on a small device, maybe you could basically accept some loss in information due to the better efficiency. Uh, but I think the rule of thumb is always better. More is better. Um, but I think nowadays there are some good tokenizer in the market that works on low frame rate and still have a very good performance. Like we could see have Mimi. Recently, there's a paper from our group, Focal Codec. I have seen it has a really good performance. So people are working on that, but I think still there is a trade-off. Uh, more
Mm.
information you add to your tokenizer, for sure you are going to have a better performance.
Yeah, so actually, right before you mentioned focal codec, somebody asked about that. Yeah. Um, there's one question. Does the survey also benchmark DMLE? Yeah, DML.
Oh, no, because at the time, actually, there is one of the things that we want to benchmark, but at the time they didn't release the checkpoints. So that's why we could not benchmark their approach. But their approach is very interesting because they don't have any encoder that basically
Yeah.
get the Mel spectrogram and try to quantize each bean of the frequency. So there is an encoder-free tokenizer. I think if you look at the table, it is the only encoder-free tokenizer,
Mm.
at
Yeah,
least
that's
at
very interesting. Yeah, for Apple work. Yeah.
yeah.
So, Pune, maybe you didn't see this question. Like, do you have any thoughts on lookup free quantization, like focal codec?
Uh, so it seems that their performance is very good, but I didn't personally work uh, with them. Maybe Mirko or Sam, you have mm, better idea, but I didn't
Ye-
work with different downstream. But it seems that the performance is very good and it is
Yeah,
very efficient.
exactly, exactly. I mean, focal codec is also work by our lab, right? So, Luca Della Libera, who work on that. And I will also was very, very surprised to see uh, pretty good results with such a simple quantizer. So that's very surprising to me. But it looks like they're working pretty well. So maybe that could be definitely an interesting direction to consider for the future. Yeah.
Yeah.
There is one more question that appeared. Were all the comparison benchmarks made after retraining on the same datasets?
Like we have two different studies. Study two is the benchmark. It means that we get the off-the-shelf tokenizer and we keep it frozen. We don't change anything. All the training happens at the probing head, like language models or the probing head that we have. And then in the ablation, we have the structure and we try to retrain the tokenizers. So I'm not sure which study you are referring. If it is the second study, the tokenizer is frozen. We don't do any fine-tuning or training.
Okay, so for the benchmark study, would we get a different result if we retrain on the same datasets?
Retrain the tokenizer on the same data set, I assume. I guess so, yeah, because we have seen that, for example, when we have the same quantizer, if we change the domain data, we have a different performance. If we change the sampling rate, we have a different performance. And basically, that is the main motivation behind ablation study. We want to make sure that if we compare two tokenizer, it is a fair comparison. So still, it is valid if we compare two tokenizer that are frozen because there's not what people are going to use for their task. There are no, like some people don't want to retrain all the tokenizer. So this is one benchmark. It is about the application of existing tokenizer. But if you want to have a really fair comparison, like why one tokenizer works better than the other, then this is the evaluation that you need to do, that we try to answer what are the different factors that actually could affect the performance of the tokenizers.
Okay, I guess maybe this could be the last question, right? So there's one
Yeah.
that appeared. Thank you for the presentation. This might be a broad question, but as an expert, what tokenizer or key aspects would you recommend prioritizing for downstream tasks in affective computing, for example, emotion recognition in LLM-based chatbots?
To be honest, for me, it seems that for something like emotions, many of the tokenizer are not performed very well. So I said when you want to have emotion, maybe there's not much difference between different tokenizer that you could use. For emotion, I think there's a still need to have better tokenizer that would capture all of this information. So I think most of these emotion-related expressive TTS or applied I try to increase the performance based on the modeling, not the tokenizer. And people use any tokenizer for emotion, I guess.
Okay, I guess this would be the really last one. If you had to identify any gaps in the survey, what would they be? Were there any questions, dimensions of variations you're still curious about with respect to tokenizer's performance?
Yeah, one thing that I'm curious and we could not explore in the survey is the comparison when you have like diffusion-based model and autoregressive models. We could not basically explore these ideas in the survey. Everything, for example, for language model is based on autoregressive. But there are a couple of works, for example, I have seen there one work from Yossi's group that tried to do the comparison between diffusion and autoregressive. But there is one aspect that I would like to see. And for sure, there's always new tokenizer, like we mentioned, DML, we could not benchmarking it. So every day new tokenizer, it means that there is a new opportunity to explore more.
All right, yeah, sounds great. Thanks everyone. Thank you very much, Pooneh. Yeah,
Thank you.
Thank
yeah,
you.
so thank you very much.
Yeah.
And I guess yeah, Pooneh, the next version is next week, right?
Yeah. Yeah. So next week we have Temos Stafiklias. I think I pronounced it wrong, but he's
Yeah.
going to talk about advance in speech recognition, pruning, deepfake detection, and learning without temporal labels. So
Yeah.
I hope that we could meet you all next week and check our website, join the Slack, and looking forward to seeing you next week.